Alright, so in this lesson we're going to be solving equations that have square roots and other radicals or root numbers. So I'm just going to do some selected examples, and then you can use the completed notes to either go take more notes, or you can try on your own and then check them and fix them. So first we're going to start off with actually solving an x squared equation, because that's going to help us relate to what to do when we try to solve a radical. So remember, we want to do everything get the x squared alone, so I'll move the 2 over. So 3x squared is 75. Divide by 3. So x squared is 25. And then at this step, so remember, to undo a squared, we take the square root, and then we'd have to do that to both sides. And then that's going to cause, so square root of squaring and square root something, so that's a 2, causes the inside to cancel. So we have x equals, and then this one's going to have 2 answers. Remember, whenever we take the square root, we need the positive and negative. All right, so then our key takeaway from this is this step right here, or I guess over here. So in order to, so x squared and square root undo each other, so an exponent and root. So when we're going to solve an equation with a root, we're going to do similar steps, so getting that root alone. So I'll move the 8 over, and then divide by 5. And then in order to undo that root, I'm going to square it, because that's going to cause them to cancel. But then now, because squaring is what I did to the left side, that's what I have to also do to the right side. So I square both sides, and then on the left side I'm left with x, and on the right side I am left with 3 squared, which is 9. Right, and we only have one solution there. And then we can always check our solutions by plugging them back in. So if I did 5 times square root of 9 minus 8, check in, does that equal 7? That'd be 5 times 3 minus 8, and 15 minus 8 is 7. So we can check our solutions by plugging them back in. If there's other operations going on inside the root, so we still want to isolate the root before we square. That's 21. And then I'll square both sides, because that undoes that root. And then I'm left with 3x equals 21 squared, which is 441. And then divide that by 3. And x is 147. All right, so now you could be a good time to maybe pause, try D, E, and F, and then check your solutions with my completed notes. Notice G and H have different root numbers, so I'll just do G as an example. So in order to cancel now a 3 that's in the root, I just raise to the 3rd power and do that to both sides. So now those are going to cross off, leaving just 2x minus 9. And then I'm going to cube negative 3, which is negative 27. And then just continue solving to get x alone. So add the 9 and get negative 18. And then divide by negative 2. And x equals positive 9. And again, I'd be able to plug that back in to verify that it makes the equation true. All right, and then for h, so just note you'd have to divide by 3 first on both sides, and then you'll end up taking to the 4th power once you do that to undo that 4th root. So you can try that one and check the completed notes. Sometimes when we solve radical equations or square root equations, we end up with what's called extraneous solutions. So that's when we have solutions that show up in our solving steps, but when we plug them back in, they actually don't work. So we're going to look at an example here. So if I were to subtract 5 and then get negative 3, and I'm going to square both sides, and that's going to cancel the root, so 2x minus 1, and then make sure you're squaring negative 3, so that becomes a positive 9. And then continue solving, and we get x equals 5. But then if I go to plug 5 back in, so 5 plus square root of 2 times 5 minus 1, we're checking, does that equal 2? So just 5 back in this equation, original equation, make it true. So we have 5 plus, and that's 10 minus 1. So square root of 9. And that'll be 5 plus 3, which does not equal 2. All right, so it doesn't work. Okay, plugging that solution back in doesn't work. So understanding why this happens, we're going to look at the graphs of square root later in this chapter, but because square roots are the undo of squaring, their graphs are actually like a parabola, an x squared graph flipped over. So it looks kind of like a sideways parabola, but we're missing the negative side because we can't take a square root of a negative. But when we're doing our solving steps, so it's because of this right here that this answer is actually thrown out and it's not a real answer. We ended up taking the negative and squaring it and making it seem like it's positive, but really that negative part doesn't exist, so we get something called an extraneous solution. So it shows up in the steps, but it's not actually a solution. These lines don't cross at all. So extraneous solution, when you do the solving step, seems to be right, but plug it back in, it's not right. And so we actually throw any of those solutions out and don't count them. All right, so we'll do one example, and then you can actually cross this example off. It didn't work out right. So I still want to get the root alone, so I'm going to subtract 3. And then when I go to square, I'm going to end up with a quadratic, so I have to square all of x minus 3. So over here it cancels to 5x minus 1. And then to square x minus 3, we do x minus 3 times x minus 3. So we have x squared, and then minus 3x is minus 6x, and then plus 9. And then we want to recognize that we have a quadratic, so there's x squared, x, and a constant. And so I want to get everything over, and we're going to solve quadratics by factoring. So it'll be minus 5x and plus 1. So minus 11x plus 10. And then I'm going to factor that. So 10 and 1, and they're both negative. So then I'm looking for what x values make each of these equal 0. And so this first one would be 10, and this one would be 1. So x equals 10 and x equals 1. But then I do want to check them for extraneous solutions to see if one or both of them actually don't work. So to plug both in, so we have 5 times 10 minus 1 plus 3, checking if that equals 0, right? Nope, sorry. We have to plug 10 back in for the x here, checking if that equals 10. So we have 50 minus 1 is 49, plus 3. So 7 plus 3 does equal 10. So that means x equals 10 is a solution. And I'm going to try 1, the other solution in there. So 5 times 1 minus 1 plus 3. Check in, does that equal 1? So x again. So 5 times 1 is 5 minus 1 is 4 plus 3. And 2 plus 3 does not equal 1. So this is an extraneous solution, so we throw it out. Extraneous solution. All right, so that equation only has one actual solution, x equals 10. All right, we can also solve equations that have rational or fraction exponents. So just as a reminder, if I want to multiply a fraction by something to get it to equal 1, I can multiply. So my goal is to make the numerator and denominator the same. So if I multiply by the reciprocal, so like 3 halves times 2/3, because I would end up with 6 over 6, and that equals 1. 4/5 times 5/4, I would end up with 20 over 20 equals 1. So to multiply by a fraction by some other fraction to equal 1, we just multiply by the reciprocal. So that would be mn over mn, which is also 1. All right, so I'm going to do a couple examples, and then again you can try on your own and do the other two with the completed notes. So before I can undo this fraction exponent here, I need to undo that 2. So x plus 3 to the 3 halves equals 27. And then, so raising to a power, that's multiplication. So if I raise this side to the 2/3 power, that's because that's the reciprocal. So 3 times 2 is 6, 3 times 2 is 6. So that's going to make this a 1 and leave me with just the x minus, or x plus 3. Right, so essentially cancel. But then since I raised the left side to the 2/3 power, I have to do the same to the right side. So raise that one to the 2/3 power. And then I'm going to turn that to a root right away. So that'd be the cube root of 27 squared. So remember, this number is the root number, and the numerator stays the exponent. And then, so I'll do cube root first. That'd be 3 squared is 9. So x plus 3 equals 9. And then we can finish solving. X equals 6. All right, and again, you should plug it back in to double check it. For C, we want to pay attention to what the numerator is. So when the m of that fraction exponent is an even number, remember there's potentially, or there are 2 real solutions. So like here, this had an exponent of 3, so there's only 1 real solution. Here there'll be only 1 real solution. 1 solution. But if the exponent is even, there's going to be 2 real solutions that I should look for. And that'd be same for this one. So if you don't remember why that is, you can go back to, it'd be the first lesson of this chapter. We talked about how an even or odd exponent affects the number of real solutions. All right, so I'm actually going to rewrite this real quick. So 2/5 equals 4. So then to undo that 2/5 power, we would raise to the 5 halves. The reciprocal, undo to both sides. That's going to cancel, leaving x minus 5. So this is where we have to be really careful. So we're going to end up taking the square root of 4 to the 5th power. But remember, when we're solving, that square root step is where I get the plus or minus for my 2 solutions. So I'm actually going to do x minus 5 equals plus or minus the square root of 4, which is 2, and then raise both of those numbers to the 5th power, so both positive 2 to the 5th and negative 2 to the 5th. And that will just give me plus or minus, so 2 to the 5th is 32. And then the positive 2 to the, the positive 2 to the 5th is positive 32, and the negative 2 to the 5th is the negative 32. And then I'd be adding 5 to both those numbers, so I'm just going to break out into 2 equations. So I'm solving x minus 5 equals positive 32, and x minus 5 equals negative 32. And then I'll solve each of those. So x is 37, and x is negative 27. Right, and again, we should double check that those actually work when you plug them back in. So if you think you'll forget to check for both answers at this step here, you could also just go ahead and turn this into a radical right away. So x minus 5 to the 2/5 would be the same as the 5th root of x minus 5 squared equals 4. So if you want to turn it to a radical, and then when you go to take the square root steps, you have to do both these, like 5 and 2, whatever order you decide to do them. So if I take the square root first to undo that 2, then I have the 5th root of x minus 5, then I'd have the plus or minus 2 there because we undid an even exponent. And then you would to the 5th, those cancel, and you'd end up with the same plus or minus 32. All right, so if the fraction exponents are throwing you off or you think you'll forget, you can just turn them to a radical, but then you have the 2 kind of things to undo here, and it doesn't really matter actually what order you do them in. Just make sure that when you if you do the square root of an even exponent, you need to consider both the positive and negative. All right, and that'll be similar for this one right here. Oops, this one right here. All right, last example, some things that might pop up. So if you have two roots on the same side, we can move one of the roots over. So 3x plus 2 equals 2x plus 7. And then now we can square both sides. That ends up canceling both roots. So 3x plus 2 equals 2x plus 7. And then get my x's together, my numbers together. So x equals 5. And then we should double check. So 3 times 5 plus 2 minus, so put it back in the original, 2 times 5 plus 7. Check into z equals 0. So 15 plus 2 is square root of 17. And then 10 plus 7 is square root of 17. So even though square root of 17 is an honest number, I know if I subtract them, they're going to equal 0. So x equals 5 is a good solution. Maybe I will do b also. So then if I add this one over, so we have a number outside. So let's get this one started. So 4x plus 28 equals 3 times 2x. So then when I go to square both sides here, I have to make sure I'm not forgetting that 3. So here I'm squaring to cancel the root, so I have 4x minus 28. Here I have to square the 3 and the square root, so I get 3 squared is 9, and then squaring the square root is, I'm going to show it, so you're doing 3 squared and 2x squared, so that exponent property I have to distribute it. And then I would have 9 times 2x. All right, and then you get the 18x and then solve for x there. And then you can plug it back in. If I have, so these ones are a little bit of challenges. So these ones are to the third. And again, it might be easier. One second. So this one's going to have a quadratic. So I'll move this over. So I have x plus 1 to the 2/3 equals 9x plus 1 to the 1/3. So I'm actually just going to raise them both to the third power since they don't have the same, so they have the same denominator, and that'll undo that. So to the third to the third. So that's like 3 over 1, 3 over 1. So over here, I'd end up with technically 6 over 3, or else those 3's cancel, so I'm just going to end up with a 2. So x plus 1 is still going to be squared. But then here, the 1/3 and 3 completely cancel, so I'd get 9x plus 1. So then we would need to work out this quadratic, and then move these over and solve by factoring like we did in other ones. This one actually, I'll go through because we're going to lose it to GCF factor. So if I do x plus 1, I get x squared plus 2x plus 1 equals 9x plus 1. And then when I move everything over, I'm actually going to end up losing my constant. So minus 9x minus 1. So the 1's will go away. And then I have x squared minus 7x equals 0. So in this case, because both my terms have x's in them, I can factor out a GCF, if you remember that from quadratics, so I can pull an x out. And then x minus 7 equals 0. And then when I do zero product property, I set each of those equal to 0. So x equals 0. And then when x minus 7 equals 0, x equals 7. And then you'd plug these both back in. So when you plug into a fraction exponent, you can, so it'd be 0 plus 1 to the 2/3, so plugging it back into this original. minus 9 times 0 plus 1 to the 1/3. Check into z equals 0. So these ones end up both just being 1s. So that answer is good. Then if I try 7, so I just want to show that if you have fraction exponents, when you're evaluating, you probably want to turn it to a root. So we're checking does that equal 0. So this would be 8, and then I'm going to turn that 2/3 power into the cube root and squared, and then minus, 64, and it'd be to the 1/3, so the cube root, and then to the first power technically, checking this that equals 0. So the cube root of 8 is 2 squared, and then cube root of 64 is 4, and 4 minus 4 does equal 0. Alright, so when you're checking your solution with fraction exponents, I'd recommend turning them into roots, and then that tells me that x equals 7 is a good solution. Alright, so go ahead and try any of the other examples we didn't get to, check with the completed notes, and then see if you can try the homework.